More than any other subject, physics is about numbers, how we measure things and how we specify things when we've measured them, and how we know how much we know about what they are. This comes down to talking about things like uncertainty and how we represent it. It's fair to say that science is not so much the finding of truth as the quantification of ignorance, that we know what we know and how accurately. Let's take as kind of a silly example. Let's say you go to the Natural History Museum and you see a dinosaur fossil, and the curator tells you that it's 65 million years old. We're 65 million, of course, using the so-called American system, is 65,000,000, so 65 million years old. You visit again on the same date 1 year later. If you ask the curator how old the dinosaur fossil is, what would she tell you? And you might think that she would tell you that it's 65,000,001 years old, because that is this year plus 1 year. But in fact, the curator is going to tell you almost certainly that it is still 65 million years old. And you might think that that doesn't keep up, but what's really going on, of course, is that it's not exactly 65 million years old when she says that. It's approximately 65 million years old. And we don't know if it is a few years older than that or a few years less than that. In fact, in geology, a few years might be the context of maybe 10 or even 100,000 years. And so coming back a year later, the fossil is still, we don't know it's aged within 100,000 years, so it isn't any older. And we need to get used to that, because we kind of like, as human beings, to say, oh wait, we know if it's a week later, then it's a week more. But we didn't know the original thing accurately enough to be able to say that when we added a little bit to it, that we have a week more or whatever. You'll see this often when people talk about things like budgets as well in state and federal governments, where things are in the billions of dollars, and then someone's like, I'm going to spend $100 more, and it just doesn't affect the budget because it isn't being tracked to that accuracy in whatever news story you're reading. When we measure any quantity, we can do so only to a certain precision. There's some finite amount below which we cannot measure the thing we're talking about, or put a different way, where we can't have two things and distinguish them if they differ by less than amount. In fact, the precision of an instrument is exactly the distance below, or whatever, let's say distance for distance measurement. It's the distance where if the difference in position is less than that distance, you couldn't tell. It would look the same to you. Imagine thinking about something like a Google map, where you and this person sitting next to you are on this Google map, and then they zoom out to the distance of a satellite. Then you and your partner would be in the same pixel, and you could not tell them the position apart. It would be the same position. We state our knowledge of a measurement through the use of something called significant figures. This is a way that we are able to quantify how bad our precision is, or how good our precision is. You should also know that significant figures is a little bit of a cheat. It's a little bit of a workaround or a kludge, because it's not entirely the best way to handle it, but it is quick and dirty, and it's the way that we're expected to at this level of a physics class. It's important to know the number of significant figures in any quantity we come out with. So there are these basic rules for counting the number of sig figs. So any non-zero digit is significant. No leading zero is significant. Trailing zeros after a decimal point are significant. And zeros between any significant digit are themselves significant. So let's do a couple of quick examples. If we had the number 1, 2, 3, 4, that is 1,234. This has 4 sig figs, because all of these are non-zero, so they count as significant. If instead I had 503, this counts as 3 significant figures, because this is a non-zero digit, so it's significant, and this is as well, and the zero that's trapped between them also counts. Let's do some counter examples. If I had 0.04501, this would be 4 significant figures, because the 4 is significant, 5 and the 1, because they're non-zero. The trapped 0 is significant because it's caught between them, but these two are not significant because they're leading. And you know because you'd never include them. It'd be bizarre to write them. And one of the things we want to keep coming back to is it would be bizarre if we could make our figures more accurate by tacking preceding zeros on them. You know that those zeros are always there, but you could add as many as you wanted. They're just arbitrary. We usually don't write any of them. You could write 15 of them. Clearly, your measurement hasn't got any better just because you chose to write 15 zeros at the start instead of writing 1 or none. If we have a number like 3.07, that's also 3 sig figs, because the 3 and the 7 are significant and the 0 is trapped. 3.007 would be 4 significant figures. I'm only doing that to show that it can be any number of trapped zeros. So the 3 and the 7 because they're non-zero, and each of these zeros because they're trapped. We could have something like 0.14500. This would be 5 significant figures because the 1, 4, and 5 are clearly significant. They're non-zero. And then trailing zeros are also significant, as opposed to 0.14510, and that's only 4 significant figures because the 1, 4, and 5 count, and there's only 1 trailing zero. By the way, I didn't even mark it here, but this one doesn't count because it's a leading zero, and this one doesn't count because it's a leading zero. The 0 before a decimal point is a leading zero, so it does not count. You should still put it. This is one of those weird cases where we contradict what your grade school teachers might have told you, but sometimes we do write a leading zero. It's much better to write the number 0.145 than just writing 0.145. Now, mathematically, those are the same. Algebraically, they're identical. Why do I say that the first method is better? Because this kind of empty space makes that dot really important but really easy to miss. And so you could end up seeing that as 145, especially in printing and photocopying. They often get lost. By writing the leading zero, we are signaling, yes, we know we don't need that 0, but it's just sort of placeholding here to say, hey, there's a number coming and it's less than 1. This isn't the kind of thing that you get credit loss for in any kind of graded situation, but it is morally superior to put a leading 0 and then a decimal if your number is of magnitude less than 1. Why is it that these two things get 2 different number of sig figs? Well, we can say that the upper one here is more precise than this lower one. It's better specified. And maybe we can see that if we do a slightly different example. So let's try and do that. Consider if we have 123, which as we know is 3 sig figs because this and this and this. Why do I say this specifies the amount that we have of precision? Because we're really saying that this number could be anywhere from as low as 122.5 and as large as anything less than 123.5. Right? It's greater than or equal to, or put it a different way, a better mathematical way, if this thing is what we're calling x, then x is really somewhere between these two numbers. If, on the other hand, we had a different set of numbers, so let's clear this out a bit. Oops. Clear this out a little bit here. And let's pick a different color for contrast now. What if we had said that y is 123.2? Something like that. Then we would say that 123.15 is less than or equal to y is less than 123.25. And that's why we say that more sig figs means more precision. We've zoomed in a little bit more on what we don't know, which is the thing lurking at the right end of our digit. Right? That's the basic idea for sig figs. That leads to some complications, or at least some potentially tricky things. What if instead, clean this up a little, what instead we had said that x is 120? Well, here we're into a typographical problem because we don't know what that means. If I say I have $120, do I mean that I don't have 119 but I have 120? Or do I mean I don't have 110, I have 120? In other words, is it true that we mean 119.5 is less than or equal to x is less than 120.5? Or is it possible, and in fact it is possible, do we really mean that 115 is less than equal to x, which is less than 125? And there's a bit of an ambiguity there because of the way that we write numbers. Could be resolved, but isn't. There's no universal convention. And so because you should never invent data, we would say that this is 2 sig figs, because that one doesn't count. Why? Because only trailing zeros after the decimal point count. And that's an important and subtle and often confusing students things. We would say, although there are 3 digits, only 2 of them are significant, because the way that's written, we really are saying is anywhere within 5 of 120. The 0 there is, remember, a placeholder. It isn't information. Why do trapped zeros count? Because if I had something like y is 4507, then we have 4506.5 is less than y is less than 4507.5. In other words, these zeros are still playing their proper role. They're not ambiguous. They're just saying, oh yeah, we don't happen to have anything in the tens place, but we have measured the tens place. With this 0, the problem is that we don't happen to have anything in the units place, and we don't know if we measured it. It gets more spectacular and maybe even worse if we put more trailing zeros before the decimal point. So if we say that our number is 4,800, now we would say that it's 4,750 is less than or equal to x is less than 4,850. And this is actually how people will tend to do that. They'll round up to the nearest hundreds. They'll say, oh, it was 300 years ago. They don't mean necessarily exactly 300 years before now. They mean around 300, within a decade or so of 300, maybe even more than that. When someone says a century, no, it was in the 14th century or whatever, you can really be down to the plus or minus 50. So we need to worry about that. If, on the other hand, what if we had 4,800.0? Well, our first case, remember, was only 2 sig figs. But now we have, well, that's significant because it's non-zero, and that's significant because it's non-zero, and that's significant because it's trailing, and that makes these 2 significant because they're trapped. And so this ends up being much more precise. It's 5 sig figs, because we would say that we have 4,800. Oops, sorry, lied a little bit. It would be 4799.95 is less than y is less than 4,800.05. We can see that's very precise. Here we've been very clear to say, no, we've measured the tenths place. And so it happens to be 0, just like the units happen to be 0, and the tens place happens to be 0, but we know that it's 0. I haven't just left it out. It's not just giving me spacing. It's actual information. And that's why after the digit counts. That's why after the digit, even trailing zeros are important, because we're specifying, no, we mean those. We wouldn't write them otherwise. If we hadn't measured them, we wouldn't write them. So if we hadn't measured if let's go one crazy one more. Let's say 4,802 zeros. Now we're saying we've also measured this place. If we don't have any data about that, we wouldn't have written it because we know that trailing zero shouldn't be there. And that is ultimately what's going on with the sig figs rules when we're trying to count things. We're trying to say, where do we actually have information? Where have we done a measurement that we could believe in? And every measuring device has some smallest size that it can. And that will tell you the furthest out sig figs you can get. All right, how do you use sig figs? Well, if you're multiplying and dividing several numbers, then the number of significant figures you have is the least precisely number. The smallest number of sig figs you have among all your multiplans or dividends or divisors, those are the most that you get out. All right, the least you can't invent information, so the least significant thing carries the day. So if I'm talking about 325 multiplied by 42, this is 3 digits and 2 digits, so my answer can only have 2 digits. Now, the actual answer, if you throw it into your calculator, your answer turns out to be 14490. But that, of course, would be 4 sig figs. Why 4? Because the trailing zero wouldn't count anyway. So we'd have 1, 2, 3, 4. But we can't invent precision. So we can't know it to 4 decimal places. That's way too overmeasured. We need to get it to 2. And so we would say here that this number becomes only 14000. That the best we can say is that's within 14,000. And they couldn't do any better than that. The same sort of things for divisors. And if we have multiple multiplans or divisors, then we end up just tracking it to the least, right? The least is always controlling. All right, unfortunately, it's a little weird if you add or subtract. When you add or subtract, then you need to take the not number of sig figs, but only the least precise sig figs, the tenths or hundredths place or whatever of the least precise figure. So they kind of show that here. If I have 18.54 and I add 106.6, notice not 106.60, but 106.6, then when I add them, of course, when we add them, we would get 125.14, but this turns out to be too precise here. So we need to limit it to only the tenths place because that's the least accurate thing we have, and so we lose the 4. All right, we lose the 400ths because we don't really know if it's there or not because we don't really know what this number was. It could have been 0.62. It could have been 0.57. We don't know what it is, so we can't talk about the hundredths place. If you need to round, we will use the universal convention that if the digit that you're throwing away, if the largest digit you're throwing away is a 5 or more, you round the number up. And if it's less than a 5, you round the number down. That means you go to the nearest value of the place you have. There are other conventions. This, like I said, is not 100% statistically balanced, and so you'll see other people try and distribute things a little bit more randomly, but we're going to go with the basic case, and we're going to say we round 5s and more up and 4s and less down. Some numbers are exact. If I say that I'm going to exactly double, right, that you have some number of coins, some number of, say, pennies, and I'm going to double them. So for every one you have, I'm going to give you another one. Then I'm multiplying by exactly 2, and that's infinitely precise. All right, I don't write the 2.0000 over there forever. I just say 2 is an exact number and multiply by it. Pi, for instance, will be exact numbers. We'll have approximations for pi, but we can carry as many digits of pi as we'd like because it's known it never stops, but it's known out to the several trillion place now. So for any practical purposes, pi is a number we can represent exactly. You'll find we'll usually just leave pi alone. And then when we have to do actual calculations with rulers and stuff, we'll multiply by the convenient amount of digits. There's sort of an exception here. You should always carry one extra place of uncertainty if you're doing multiple steps, if you need to do some multiplications and then add something and then take the total thing and divide by some number, and you're doing all these extra steps, you should take everybody to one extra decimal place. And then at the very end, figure out what the number should have been and round to that number of sig figs. This will minimize the buildup of rounding error. I will say, having gone through all of that, the AP committee is generally pretty good, and they say if you're within one number of the correct number of sig figs at the end, then you get credit. And it turns out that all of their problems are like 2 or 3 or 4 sig figs. So if you always round to to 3 significant figures, then you are almost certainly going to be correct, or at least you're going to get full credit. All right, let's rank in order from the most to the least the number of sigs in the following numbers. For example, if B is more than C and C is the same as A, and A is more than D, then you would choose B is more than C is equal to A is more than D. And we'll use this notation a fair bit in the class, so it's probably useful to get used to it anyway, but it's pretty easy. It's traditional for most people to say we'd also group. We'd say B is more than C equals A, and that companion thing is more than D. And so maybe here I'll immediately go and group before we even look at the problem and say that's what we're talking about. And the easiest thing here is to just figure out how many we have. So working backwards, we have 1, 2, 3, 4, or 4 sig figs. And then here we have 1, 2, hey, that's 1 as well. So we have 3 sig figs. Over here we have the non-zeros are these 2, and the other zeros don't count because they're leading, so this is only 2 sig figs. And here we have 2 non-zeros, and then we get into this weird thing here. And our convention is, without any further information about it, we should not count that, so these are also 2. So in this case we have B is equal to A, and it's not equal to D, so it has to be, by the structure, it has to be this one. And we can check and say D is more than C is more than the other 2. All right, we're going to cover something called scientific notation. You're probably familiar with it, but if you write very large numbers, which are numbers much greater than 1, or very small numbers, those much less than 1, the writing of them is very cumbersome, because it's not very clear to see how many sig figs are involved, and comparison can be really awkward. For instance, the distance from the Earth to the Sun is this, where it's 146, and then 1, 2, 3, 4, 5, 6, 7, 8 zeros. If I wanted to try and say that, I'd have to go here and say 1, 2, 3, comma there, 1, 2, 3, comma there, 1, 2, 3, comma there. Nothing, thousands, millions, 149,600,000,000 meters. Likewise, if we look over here, we have the size of bacterium looks to be 5 millionths of a meter. Those are awkward. Also, it's very easy to miss a 0, or if comparing two things, you might be hard to say which number is larger because they've got lots of zeros in them, and so you've had to actually place them side by side. It's awkward. All right, they're annoying to write with. They're not hard to handle mathematically. That we don't care about them algebraically that way. They're just annoying to write. So we use something called scientific notation. We express the number as a small number times a power of 10. So for instance, we would take our first one, and that is 1.496 times a 1 and 11 zeros after it. I should verify that, but so 1, 2, 3, 4, 5, 6, 7, 8, 9, 11 zeros. And we know that 1 with 11 zeros after it is 10 to the 11, so we would write this as 1.496 times 10 to the 11. And likewise over here we have 5 times 1 millionths, and we can go the other way and say 1, 2, 3, 4, 5, 6, that's 10 to the minus 6, so that number is 5 times 10 to the minus 6. Right? Again, you've probably run into this, and if not, it's not that bad. You just have to sort of get used to it. Maybe the first time through, think about it kind of carefully, but you'll rapidly get it. It's not that bad to see. The power of 10 that we use is called the order of magnitude. So the order of magnitude of the first one was 11, and of the second was minus 6. And in scientific notation, we only write significant figures in that number so that every digit written is assumed to be significant. Notice the order of magnitude is not part of the significance. All right, so the 2 digits here, if we had, going back to the number we had here, 1.496 times 10 to the 11, we see that, well, it's 1, 2, 3, 4 significant figures. We don't include this in the significant calculation at all. It's an exact number. It's 10 to the 11. We've separated out. It has as much significance as we would need in our multiplication, and so this would be 4 sig figs. And the other one, which was 5 times 10 to the minus 6, we have 1 digit, because again, this doesn't count. It's exact. And so this is only 1 significant figure. One reason we do that is because changing the scale shouldn't change our precision. And we do converting units later, we'll see how that plays into it. But it has to be that the exponent cannot have an impact on the precision, because we can just rescale to get a different one. In scientific notation, technically, the prefactor needs to be more than or equal to 1 and less than 10. In other words, if you were to write 0.1496 times 10 to the 12, that's actually the same number as that, but this is not scientific notation. That's just a convention. There's no deep morality in it, but it is conventional that we have a number which is more than or at least equal to 1, that we don't have any fractions as the prefactors. All right, there's a video linked on the website called Powers of 10 that is very much worth watching. It basically gives you scales in terms of distances for things starting at 1 meter, which is the base scale we'll be using a lot, and then going up by powers of 10 every second. So a second later it's 10 times further out, and 2 seconds later it's 100 times further out, and so on, to give you some scale of the universe in which you live, and you are strongly encouraged to watch it. It's not that long, and it's pretty impressive how they illustrate what's going on. All right, how do we convert a number into scientific notation? This is just summarizing what I said before. If the number is greater than 10, move the decimal point to the left until there's only 1 digit remaining, and the remaining number is then multiplied by 10 to a power, and the power is the number of times we've moved the decimal places. All right, and they show what's going on here. For a number that's less than 1, they mean here, by the way, a positive number less than 1. If the number is negative, we're only talking about the magnitude or the absolute value here. So for a number less than 1, move the decimal point to the right until it passes the first digit that isn't a 0. The remaining number is then multiplied by 10 to a negative power, where the power is given by the number of spaces you've already moved. So for instance, here we move over 6 times, and so we have 10 to the minus 6. It'll take a little bit of practice, but it isn't that hard.